temperature. Until the temperature output is very far.
Yes, sir.
The temperature winds.
All right.
This means that
Hello, everyone. Welcome to this IEEE event. I'm pleased to introduce Dr. Kumar Vijay Mishra. He'll be presenting on signal processing for integrated sensing and communications.
Thank you. Okay.
Okay, thank you. Good evening, everyone. Thank you very, very much for the invitation to the Santa Clara Valley Section chapter of the IEEE Communication Society. And in this distinguished lecture, I'm going to talk about one of the very actively investigated research topics in recent times in signal processing, remote sensing, communications. And we'll see in the lecture that this is a very broad area of research nowadays. It's very difficult to summarize the entire gamut of activities that are happening in this area of joint radar communications or ISAC as it is called, integrated sensing and communications, in this roughly 50-minute lecture. So my goal today is first to give you an overview of the history and context of ISAC research, and then provide some examples. And as we move forward in the lecture, we'll start with a very theoretical example, and then we'll go to a more practical example, while we will also explore different design topologies in ISAC. I would like to explain several terms that are associated with this area of research, especially for people who may be new to this topic. So that's the overall outline of this work. So Behnam already introduced me. I'm not going to read everything about myself here. I just want to emphasize that apart from my role at the University of Maryland, College Park, and Army Research Lab, I'm also a technical advisor to these very promising startups. First is Hertzwell, which is Asia's first automotive radar startup based in Singapore, and I've been associated with them right from their inception in 2018. And second is Aura Intelligent Systems, which is based in Boston. It's a 5G imaging radar startup that is using 5G waveforms for imaging applications, somewhat related to what we are going to discuss today. So my primary interest lies in radar, and I explore its connections with signal processing, communications, remote sensing, and electromagnetics. I would like to acknowledge a number of my colleagues whose collaborative research will feature in this talk, from Army Research Lab, University of Luxembourg, Industrial University of Santander in Colombia, as well as Army DevCom and the National Academies of Sciences, Engineering, and Medicine, which is based in Washington, D.C., for funding most of this research. In my talk, I like to put snippets from my favorite science fiction TV shows and movies, just to keep things interesting, where the characters are discussing radar. So you will see throughout this presentation, and that is, as I said, just for entertainment purposes. But the snippet that you see on this slide is very much related to the topic we are going to discuss today. This scene is from a very popular Apple TV Plus show, For All Mankind, which is based in 1960s, an alternative fictional historical timeline. And it's about a bunch of NASA scientists. And in this scene, they are discussing the effect of solar flares because of heightened sunspot activities on ground-based communications networks. Apparently, those solar flares can actually cause some kind of jamming in communication networks on the ground. Indeed, if you go back to 1960s and look into the technical literature that was published at that time, there used to be an IEEE journal. It has been discontinued for a while. IEEE Transactions on RF Interference. And many papers that were published in that journal around that time, they were exactly about this topic. Here is an example. That is the interference from solar flares on ground-based communications network. This is a very good example of natural interference on communications. Today we are going to discuss man-made interference, that is interference from other emitters, radar, navigation, timing, all other types of sensors on communications, and vice versa. Of course, research on RF interference has been around for a while. So we just saw one example in 1960s. NASA did some research in late 1970s on this topic, but it was really in mid 1980s that this topic became very important. The reason being, at that time, US military was installing this radar that operates in UHF VHF band, that is the lower frequencies, which we call as FOPEN radar or foliage penetration radar. That's a radar that can detect intruders who are hiding in dense vegetation areas like forests, etc. So FOPEN radar is very useful, has been in use in many countries, but in 1980s when US military was installing this radar, then they noticed interference from TV and broadcast stations at the receiver of FOPEN radars, because throughout 60s and 70s there had been a proliferation of TV and broadcast around the United States, and this became a major source of nuisance for FOPEN radar receivers. Since the transmit bandwidth is very wide for that particular radar, engineers came up with a simple solution, that is, you put notch filters at the receiver and remove the interfering frequencies. It wouldn't cause a lot of signal distortion or loss of range resolution just because the transmit bandwidth is big enough. So clearly these kind of solutions have been around for some time, but it is really in last 10 years that we have seen a lot of work going on in the area of spectral coexistence, spectral crowding problem, spectrum sharing, and so on. So first, let's look into the causes of what are the recent driving factors behind this research. So there are two primary motivations. The first comes from the communication side. As you can see from this graphic that I've taken from some industry sources, the current wireless communications trends, they indicate that billions of devices, they are already connected, and this number is going to rise dramatically in the near future. So when so many devices are connected, there is obviously a huge inflow of data, huge exchange of data between these kind of devices. At the same time, there are expectations from future wireless communication services, 5G or beyond 5G networks, to support very futuristic applications related to infotainment, gaming, and so on. And all of these applications, they again require very high data rates, which the current sub-6 gigahertz protocol, which is our conventional wireless communications regime, they are unable to support. So how can we meet this challenge? For that, we turn to Shannon's famous capacity formula as a guide, which tells us that the capacity C, which dictates the data rate, is governed by three factors. The first is lowercase n, which is the number of orthogonal or non-interfering resources, could be the number of time slots, number of subcarriers, could also be the number of transmit and receive antennas, which we know is the concept of MIMO communications. So you increase n, that has a bearing on capacity. Second factor is signal to interference plus noise ratio, or SINR, but you will have to increase it a lot to see any appreciable increase in C, because they have a logarithmic relationship with each other. So we come to the third factor, which is bandwidth W. Wider the bandwidth, higher will be the capacity. So clearly we can move to a spectral regime where bandwidth is high. However, that is not very easy, because this is a limited and a scarce natural resource. Electromagnetic spectrum is limited as we know it, and a lot of it, especially at lower frequencies, has already been allocated to various other emitters or applications by international and national regulatory agencies like International Telecommunications Union, or in the US, FCC, Federal Communications Commission, and so on. So it's difficult to allocate that spectrum just for one service. Another limitation here is that already sub-6 gigahertz spectrum is crowded. So we can move to millimeter wave, or the so-called sub-terahertz regime, as you can see from the graphic at the bottom left, which I've taken from the Ericsson's white paper published in 2022. So it tells us that the traditional wireless communications regime is sub-6 gigahertz, where, it's already sub-6 gigahertz, so you can't have bandwidth like 6 gigahertz, but as you move to millimeter wave band, depending on which country you are in, you can have anywhere from 4 to 7 gigahertz of contiguous bandwidth. So that's a lot, and that can have a significant bearing on the capacity. And when you move to the sub-terahertz band, in certain regions, you can get 15 gigahertz of contiguous bandwidth. Currently, ITU has allocated spectrum until 275 gigahertz, and very actively discussions are underway to allocate spectrum beyond that. So it's very attractive to use these parts of the spectrum. But then there are so many wireless communication service providers, and everyone wants access to these wider bandwidth. So it's difficult to allocate this to just one service. And that challenge is also not new. I've taken some of these headlines right from 1980s to until very recently, where you can see that wireless communication service providers, especially in industry, they have been asking government for wider bandwidth to be allocated to them, and they have been contesting for this wide bandwidth for a very long time. But again, because there are so many service providers, it's difficult to satisfy each one of them by allocating a very specific spectrum just to one of them. Apart from this, we have other applications also which need wider spectrum, not just communications. So the second motivation comes from the radar industry. Although in radar remote sensing, if you look into the IEEE literature, there has been classification of IEEE radar bands. Pretty much every major part of the spectrum has been in use by radar for a long time. Even the so-called millimeter wave or the sub-terahertz spectrum, at least in sub-terahertz, we have about 25 years of research for radar application. So that part is not new. Radar engineers have been using various parts of spectrum for a while. But recently, there has been a new development that is in autonomous vehicles. As you can see from this graphic, modern autonomous vehicles, they are highly sensor driven. They are equipped with several sensors like radar, ultrasonic sensors, RF, GPS, camera, LiDAR, and so on. And the goal of these sensors is not just to guide the driver in a crowded and challenging traffic environment, but also to monitor the general health of the car. For example, we have sensors for tire pressure and various other functionalities, and sometimes also to monitor the physiological behavior of the driver and other occupants of the vehicle. For example, we have in-cabin sensors to measure the heart rate, respiratory rate, and other vital signs of the occupants of the vehicle. So these vehicles, they are highly sensor driven because for autonomy you need that kind of functionality. But if we focus just on the autonomy aspect, forget the tire pressure sensors and those other kind of devices, then to enable autonomy, chiefly three sensors are very common. First is a high-resolution camera, provides a very good visual, also have a lot of semantic information in its files. But in low visibility conditions, whether in the night or in the presence of precipitation, rain or snow, then its performance worsens. Also, it does not measure Doppler velocity directly, because if you're on the road, you would like to measure the velocity of other vehicles. But a camera wouldn't do that directly. Rather, it would infer it indirectly by looking at the changes in the vehicle movement across different frames. So that is not very accurate. So we move on to the remote sensing based sensors, that is LiDAR and radar. So LiDAR operates in optical range, as a result of which it has higher resolution. The reason being, for people who may be familiar with remote sensing, may recall that wider the transmit signal bandwidth, higher will be the resolution of that sensor. By resolution, we mean the ability to discriminate two very closely spaced targets. So in optical regime, bandwidth is very wide. That's where LiDAR operates. So it has a very high resolution. However, the issues with LiDAR are its cost. It's very expensive. A few years ago, General Motors had released a white paper where they stipulated that the cost of these remote sensing sensors in batch production should not exceed $100, and LiDAR does not meet that benchmark. Although there are efforts to bring down the cost, but we are still not at that benchmark that the automotive industry wants. Second issue is that it is sometimes mounted outside the main body of the vehicle for aesthetic reasons. Some vendors may not like that. And the third is that it usually has a mechanical scanning, mechanical scan, which is again not warranted, because in case of radar, you can do with electronic scanning without actually moving the sensor. I must mention there are efforts to make electronically scanning LiDAR, but they are all in research domain. There are some papers that have come out in past few years, but I haven't seen commercial or widely used implementation so far. So we come to radar, and the advantage of radar is it's low cost. It meets that $100 benchmark, for example, and it measures Doppler velocity directly. Unlike a camera, it operates on Doppler principle, as we know. So radar sends out an electromagnetic wave, which is characterized by its amplitude, frequency, and polarization. And when that wave interacts with a target of interest, all these three properties change. So when the signal comes back at the receiver, by monitoring the change in these three characteristics of the wave, we can gain valuable information about the targets. For example, if you can see how much time it has taken to come back, that is indicative of the range of the target. And if we can find out the modulation of the wave, additional modulation, that is directly proportional to the Doppler velocity of the target, and so on. So it measures Doppler velocity directly, day or night, doesn't matter, radar still functions, and at millimeter wave, for the range that we want it to function, like 200 meters, it doesn't suffer sufficient attenuation either in the presence of rain or snow. So even in harsh weather, you can get a good sensing using a radar sensor. But the issue with radar is it operates in microwave regime where bandwidth is limited, unlike a LiDAR. That means it has a poorer resolution. The only way to enhance the resolution is if you allocate more bandwidth to radar, or you move into, you operate the radar in a regime where a lot of bandwidth is available, like millimeter wave or sub-terahertz and so on. But we just saw in the previous discussion that it is difficult to allocate bandwidth just for one application. Now, on top of that, we have the concept of connected and automated vehicles. So a lot of these autonomous vehicles, they are software controlled. They are supposed to talk with other vehicles, with satellite, with infrastructure, and a host of other devices, what we call as V2X communication. And as a result of this, they generate a lot of data, which the current sub-6 gigahertz short-range protocols like DSRC or CV2X, they are unable to sustain. So again, if we go back to the communications discussion, if you have to sustain a lot of data, then you have to allocate again more bandwidth. So we have this problem that in order to have a high resolution as well as to stay connected, autonomous vehicles, they need wider bandwidth, which is limited. So both communications and radar industry, they have these recent or new needs for wider bandwidth to support various kinds of futuristic applications. Apart from that fact that these two are the major drivers, there are a lot of other new applications of radar and communications, which is leading to the problem of spectral crowding. As you can see from the table here, pretty much every IEEE radar band today has some coexisting communications service within that band, and this problem is only worsening as new types of communication protocols or new applications of radar or new deployments of radar devices, they are getting explored by either industry or by other researchers. In fact, this problem is not just technical, that is, if two emitters are operating in the same band, then they will cause interference to each other. But it also has a lot of policy and legal issues. So there have been two very famous court cases recently. Some of the headlines I've put here. So one of them was in 2021 when FCC allocated slivers of sub-6 gigahertz band to some unlicensed users. That means anyone could transmit in sub-6 gigahertz, which is a highly valuable band for wireless service providers. And as a result of that, AT&T sued FCC with the contention that this kind of allocation is going to worsen their wireless services which operate around those unlicensed bands. Another court case was in 2022 when FAA, that is Federal Aviation Authority, asked Verizon, which is another wireless service provider, to stop transmitting their 5G services near the airports because it was causing interference to another device that is used by airlines for takeoff and landing, and this device is a C-band altimeter. In fact, this example tells us that the problem is not just limited to communications and radar, it could affect other devices as well. So the C-band altimeter, ultimately they arrived at a compromise that the C-band altimeter will be fitted with these notch filters to remove these 5G interfering frequencies. So there are other applications as well. radio astronomers have been complaining about interference from communication satellites, which are hindering their clean sky observations. Meteorologists are complaining about interference from Wi-Fi, which has been sometimes misconstrued as a false storm or tornado warning. So this problem is now pervasive. It is affecting a lot of players in this who wants access to more spectrum. And that's why there has been a lot of talk about, can we develop some systems so that they can intelligently share the spectrum while operating in the same channel. So recognizing these technical, legal, policy implications of this problem, DARPA in 2012 initiated this program called SPARC, that is to develop spectrum sharing solutions for S-band military radars and S-band military communications. Following the success of that program, National Science Foundation started this investigation across all the bands, and they have launched a number of programs on spectral coexistence, spectral crowding, all these other problems, some of which I have listed here, like SWIFT, PAR, NERDS, etc. And every few months these days, I see a new call from NSF on this particular issue, or some aspect of this issue on spectral coexistence, spectral design, etc. So clearly, this problem is very important nowadays. When we started this work in 2015, there used to be one new paper on this topic every 6 months, and nowadays every hour I see on my Google Scholar alert that new papers are minted out on some aspect of this problem pretty much every hour throughout the day. So problem is very important, and if we have to look into last 12 years of research since the start of DARPA SSPARC program, what kind of spectrum sharing technologies have been developed so far and in which direction this area is going, then if we have to very broadly classify them, if you want to share the spectrum, one way could be that you share the same hardware, that is communications and radar, they have the same transmitter, same receiver, use the same waveform, and then let the receiver perform the functionality of both radar as well as communication. So that would be a very ideal way of sharing the spectrum. So if we approach the problem from the hardware sharing perspective, then one very simple classification or broad classification will be as shown in this figure, which I have taken from one of our papers that appeared in IEEE Signal Processing magazine. So you can have 4 topologies. When the receiver and transmitter, none of them is shared between radar and communications, you get solution A, where radar and communications, they transmit independent of each other in the same part of the spectrum. Obviously, there is going to be interference at the receiver. So most of the novelty or most of the research under this category of spectrum sharing solutions lies in developing new receiver signal processing algorithms to mitigate the mutual interference, largely in the digital domain. This is called spectral coexistence. This kind of approach is usually adopted by legacy systems where it will cost a lot to redesign a transmitter, receiver, and redeploy all of them, because these systems could be very expensive and a number of those units have already been deployed. So we want to work mostly on the digital side, at the receiver side, just try to mitigate the interference. And this was a very popular approach during the early days of ISAC research. Everything else is called spectral co-design, where some part of the hardware is shared. A very general example is solution number D, which I have taken from one of our papers for automotive application in a vehicular scenario. So here you have a red car that is a common transmitter. It is transmitting a radar waveform that is modulated with communication symbols. That waveform then interacts with other cars in the environment, which we'll call them as radar targets. For example, the blue car or the yellow car. When the signal is reflected from these targets, it is intercepted by a common receiver which is on a gray car. And the goal of signal processing at this receiver is A, to extract valuable information about the radar targets, for example, the location, Doppler velocity, etc. of the blue and the yellow car, as well as to decode the communications message sent by the red car. So it is performing this dual functionality of radar as well as communications receiver. And since the transmitter and receiver, they are not on the same platform, not on the same car, for example, we also call this a bistatic system. In fact, as we'll see later in this talk, In automotive scenario, usually we want to explore bistatic or multistatic cases, because it's very likely that in a crowded traffic environment, when you're transmitting, when the signal is reflected, it can be intercepted by some other cars as well. So it's a more general scenario. Now, obviously, if there are just 4 of these solutions, and given 12 years of research, people would have developed solutions for all 4 of these topologies. But that is not the case. As I mentioned earlier, this is a very broad classification, but we can approach this problem in a variety of ways. So we already saw, based on hardware, what kind of other topologies could be there. Then based on waveform, waveform could be the same waveform, or both radar and communications could use different waveform, or it could be the same waveform that is shared on time slot basis for radar or communications functionality. Now, based on location, so we just saw bistatic case. Co-located means transmitter receiver at the same location. You can have multiple transmitters, multiple receivers for radar and communications. They may or may not be networked. So you get a more distributed kind of topology, which is very popular these days, distributed ISAC. Often when we are working on ISAC solutions, while we would like to optimize the performance of both radar and communications, there could be some applications where we are primarily interested in just radar performance, and we can tolerate some deterioration in the performance of communications. Those solutions are called radar-centric. Vice versa, you can get communication-centric solutions as well. And then there's this very interesting example of opportunistic ISAC, and I'll show an application towards the end of this talk on opportunistic ISAC, where there is already communications infrastructure or radar, and you want to use that communications infrastructure for radar purposes without without making a lot of change in the hardware or the configuration. So essentially, you want an existing communications infrastructure to double up as a radar sensor as well, and you can have vice versa as well. So that's called opportunistic ISAC. Then on top of this, there are several other specialized ISAC topology. In some cases, you would like to leverage deep learning. We'll see if there is time. I'll give an example where a lot of deep learning is involved. Otherwise, in opportunistic ISAC, we'll see an example of learning-based ISAC. Both radar and communications, they are in MIMO configurations. So you get MRMC, joint MIMO radar, MIMO communications, in-band full duplex. There is a lot of work these days, and sometimes I do a lecture just on that one topic, which is using intelligent surfaces for ISAC. So that is IRS-aided ISAC. Depending on which part of spectrum you're in, usually you get a different solution. So millimeter wave has its own implications, terahertz. I've also seen some works on joint visible light communication, VLC, and visible light positioning. There are also some works from the quantum community, joint quantum communications and quantum sensing. In fact, there are 15 different IEEE societies which have published literature on ISAC or have some working group that is devoted to ISAC solutions. Even non-IEEE societies like American Meteorological Society, International Union of Radio Science, etc., also have some technical working group on spectral crowding problems. So this problem is quite broad. Now, that is not very surprising because we have so many different types of radar applications. At the same time, we have so many different types of communications protocols. And when you want to share spectrum between any two of them, usually it leads to a new or a bespoke solution. That's why we have this abundance of literature on ISAC, and it's still growing because there are so many different functionalities that radar performs or communications, and sometimes you want to optimize just that one particular functionality for both of them. Usually you get a new solution. So as I mentioned earlier, it's difficult to summarize all of them in this lecture. Typically, I and my colleagues, we do 4 or 5 hour tutorials in different conferences to give a more in-depth overview of all of this. But I would like to provide some examples now. So we have seen 3 main topologies: spectral coexistence, co-design, and opportunistic ISAC. Let's take at least one example each to explain these topologies. And as we move from coexistence to opportunistic ISAC, as I mentioned earlier, we'll also move from a very theoretical example just to show how new signal processing theories they come into play when we are dealing with ISAC problems, to a very practical example as well. In spectral co-design, it depends on how much time I have, maybe we'll take 2 examples or just 1 example. So let's start with spectral coexistence. So here we would like to recall that in spectral coexistence, both radar and communications are transmitting independently. There's no coordination between them. So at the receiver, there's going to be interference. And most of the signal processing research is about how to extract information that is useful for communications and radar from this overlaid signal. So in this context, for past 3 years at US Army Research Lab, we have been working on this very interesting problem called dual blind deconvolution. To understand what this problem is about, let's recall how conventional radar and communications work. In a conventional radar system, we transmit the waveform, so we know the waveform. What we don't know is the information about the radar target, that is the unknown. So for the purposes of this segment of the talk, I'll call this as a radar channel, that is the target information. Then the received signal is the convolution of the known transmit signal and the unknown radar channel. And from the received signal, we would like to estimate the radar channel given the knowledge of the transmit signal. This problem is the standard deconvolution problem, which has been explained by Norbert Wiener himself in 1949. So deconvolution, if you look into radar signal processing, most of it is standard deconvolution. Now consider a case where we don't know the transmit signal as well. This could be a case when a hostile entity is transmitting the waveform, and that's why you don't know that signal. Could be a case of passive coherent localization, where again we don't know the transmit signal. So you will have a situation at the receiver where you have this convolution of unknown transmit signal and unknown channel. And by looking at, yes?
I wonder why you are not using a sample from the transmitter to the receiver?
Yes, because if we have that information, it makes the problem easier, clearly, if you have that direct information. But if it's a hostile entity that is transmitting, then we don't know which signal is that. So there can be
So you are assuming that you don't have a sample?
Yeah, we don't have that. But your question is very good, that yes, in some cases you can have that information. We start with an assumption how less we know about the signal. And then as you add more information, obviously the problem becomes easier. So in that case, you will have a situation at the receiver where you don't know both of these convolvents. All you have are the received signal, and you would like to estimate both of them. This is what we call as blind deconvolution. It has a rich heritage of research in signal processing literature right from 1970s. But in the last 10 to 15 years, there has been a lot of work in this area, especially with the use of sparse reconstruction techniques to actually provide more concrete guarantees for the recovery of both signals, both convolvents. Now consider communications. Communications, in traditional communications, the problem is slightly different. It's the transmit message that is unknown, and we estimate the channel, communications channel, a priori. Then at the receiver, you have the standard deconvolution problem. With the knowledge of the channel, we try to estimate the transmit signal. However, as you go up in the band, like millimeter wave and terahertz, coherence times are very short, channels are very dynamic, especially in vehicular applications, the channels could be very dynamic. Even you estimated the channel a short while ago, it may become outdated very quickly. And you will have a situation at the receiver where you don't have the knowledge of both the channel as well as the transmit signal. So in other words, blind deconvolution. In a spectral coexistence scenario, you will get both of these signals overlaid. So you will have a situation where you have the received signal where you don't know 4 of these convolvents. This is what is known as dual blind deconvolution. By extension, you can also have n-tuple blind deconvolution. So just for the sake of simplicity, I'll skip n-tuple blind deconvolution, but I'll provide a reference where, from one of our papers where you can find more information about that. So let's just stick to dual blind deconvolution. So the first equation here encapsulates the problem where I have this received signal y. It is the superposition of 2 convolutions. Subscript r is for radar, c is for communications, x are the transmit signals, h are the channels. By just the knowledge of y, it is impossible to estimate all 4 of these variables. because there will be so many combinations of these variables that will match to the same Y. So in other words, this is an ill-posed problem. In order to solve this, if we look into blind deconvolution literature, then there have been a lot of developments, as I mentioned, in past 15 years. Usually, if you have some knowledge of the structure, that can help you in solving this problem. So that's our line of attack while solving this problem. We start with the assumptions of what are the standard channels for radar and communications. So we start with the radar channel model that is given in the gray box. We assume there are L targets. Each target is characterized by unknown reflectivity alpha, which is indicative of its size, shape, or material. The delay time tau r, which is directly proportional to the location of that target with respect to the radar receiver, and Doppler frequency nu r, which is directly proportional to the Doppler or radial velocity of the targets. It's a standard radar target model. For communication, similarly, we assume Q paths and again a delay Doppler channel. For the transmit signals, for radar, we assume it's a pulse Doppler radar. That is, it is transmitting a train of unknown pulses, ST. So we don't know the ST, but we know how many pulses it transmitted because we are counting the pulses at the receiver. So it transmits P pulses. Those are the number of pulses we admit at the receiver. Then for communications, we assume it's a standard OFDM signal, and we would like to estimate the message GP. Note that we are only going to estimate the message GP. We are not going to map it to a constellation or decode it because that part is standard. Since 1990s, there has been a lot of work on blind decoding, blind equalization in communication. So once you estimate GP, you can apply those kind of algorithms to further decode it. Here we are only interested in first estimating GP. So when we take all of this structure, put it in the first equation, discretize the signal, then after a few pages of tedious algebra, you get this last equation that is shown here. You can find more details on how we derive this in our paper that appeared last year in the IEEE Journal of Selected Areas on Information Theory, JSCIT. Now, in this equation, we have number of unknowns. We have the transmit signals S and G that are unknowns and all the channel parameters that are unknown. So even though we have given some structure to the signal, we still have to find some algorithm to actually estimate these unknown variables. Here is how we are going to proceed. We make the following observations. First is that the channel parameters, they are continuous valued. So what I mean by this is, if you take Doppler velocity, typically in a radar receiver, you can estimate Doppler velocity through spectral estimation techniques. You apply DFT and then see where the peak of in the spectrum falls in which bin, and that can be converted, that frequency could be converted to Doppler velocity. But then that means you have to bin the spectrum, you have to discretize the spectrum. But the velocity is continuous valued. A fighter aircraft doesn't fly at a velocity 300 meter per second and after that only 310 meter per second. It can have any value, 305.69 meter per second. But if you're binning the spectrum, you are inherently assuming that it can, even if it is flying at 304 meter per second, you are only going to detect it as either 300 meter per second or 310 meter per second if the bin size is 10 meter per second. So we want to estimate this continuous valued parameter. So all those techniques for spectral estimation where this kind of discretization is assumed, that goes out of the window. Second aspect is we are going to exploit the fact that the channels are sparse. There are only L targets and Q paths, and most of the time this kind of assumption is satisfied for most of the radar and communications channels. So L and Q, we have just only those paths or targets compared to the number of samples we are going to sample and compared to the number of pulses we are going to admit. Third is a very important observation here. We'll put this mild restriction in order to solve this problem. We'll put this mild restriction on the transmit signals. So for channel sparsity, for transmit signals, we'll restrict them to lie in a low dimensional subspace. This is what is known in blind deconvolution literature as the lifting trick. What it does is that if you have these systems of equations, that means received signal and all these unknowns, solving that system of equations could be tricky. So this lifting, because they are underdetermined system of equations. Now lifting trick, what it will do is it will convert that solving a system of linear equations into a problem where you have to recover low rank matrices. And those low rank matrices, they encapsulate all the unknowns. So that's what we are going to do. So after again a few more pages of tedious algebra, we get this compact discrete signal model that is shown here. That is your measurements, discrete measurements y. They are superposition of two linear operators, aleph r and aleph c, that is for radar and communications, each of which is a function of a low rank matrix zr and zc, which encapsulate all the unknowns of radar and communications channels respectively. Now, how to solve this problem? Before we go into that, I would like to draw your attention to the structure of these low rank matrices. So as you can see from this last equation, these matrices have these exponentials inside them. That is e to the power j and then some phase. Yes?
I don't see here the noise component at all. So you're assuming for the time being no noise.
For the time being, no noise, yes. But I'll explain how you can take care of noise in a bit. Yes. Yeah, very good observation. I mean, I won't cover that part, but I'll explain when we come to that. Okay. So you can see these complex exponentials in the structure, and this is going to be very useful when we try to solve this problem. Now, when we have these complex exponentials involved, in mathematical language, we are dealing with trigonometric polynomials, because you can write a complex exponential in terms of sines and cosines using the Euler's formula. In fact, DFT is a very good case of a trigonometric polynomial, which we use all the time, but we actually don't call it trigonometric polynomial in signal processing. But now we'll deal with this term trigonometric polynomial in a more general way. So how do we solve this? It's a sparse reconstruction problem, except that the sparsity is not just in one domain, it is a little bit more complex. It is in both delay as well as Doppler domain. Normally, when we have sparse reconstruction problem, we apply L1 norm minimization. Now here it is a little bit more complex in higher dimension, and then both radar and communications, they are superimposed. So we are going to use a generalization of L1 norm, which is called atomic norm. So it's an analog of L1 norm, but applied to arbitrary basis. It was proposed about 12 years ago, and its applications in spectral estimation have shown very good results in recovering continuous valued parameters, which is what one of our goals was earlier, right? So atomic norm minimization, the standard atomic norm minimization, if you write that a primal optimization, its main optimization problem, directly you can get its semi-definite program, which means you can go to a computer and write a MATLAB code or whichever is your favorite language and then solve it. But here it's a little bit more complex. It's not a simple atomic norm minimization because you have sparsity in radar and in communications. So what we are going to do, we are going to minimize the sum of the atomic norms of radar and communications. So we call it Soman minimization. That is the equation you see in this box. That is minimize the sum of atomic norms. So apart from the fact that it is sum of atomic norms, because sum of two norms is also a convex function. Second aspect is that it's multivariate. It's not just one dimensional, it's in both delay as well as Doppler. That's why Soman, sum of multivariate atomic norm minimization, subjected to the measurements. So we don't have a very straightforward way to get semi-definite program for this. And if we had just a standard atomic norm, then you would have gotten the SDP very quickly. It's straightforward. So how do we approach and try to find out the SDP? Yes.
What is the advantage of this approach over simple convolutional techniques? Where you have the string, you are running it across, one maximum, second maximum?
Because it's not simple convolution, it's blind deconvolution. We do not have information about all four variables. So it's ill-posed. Yeah. If we knew two of the operands, convolvents, then also that technique could have been used. But now this is dual blind. Yes. Okay, so we have this primal optimization problem. We would like to get its SDP. This is where we come to that theory of trigonometric polynomials. So this example is intended to show how some new theories, they come into play in ISAC problems. So for people who may not be familiar with this, a very quick primer on trigonometric polynomials, but a specific aspect of that is positive trigonometric polynomials. That means the value of the trigonometric polynomial is greater than 0. Yes?
Actually, this technique that you showed is a technique that the enemy will use, because the enemy maybe doesn't know what is the thing, so he easily can also use it.
Yeah, so that's why I mentioned earlier that, so by the way, problem came from US Army, and I mentioned earlier, if a hostile entity is transmitting, then how to do this. So we are the first ones to do this. Literature is openly published, so yes, if they want to replicate, they can, but we have done this first.
So this is why the importance of a sample that can be delivered wirelessly, so the enemy doesn't have access to it. So you have an advantage over the enemy if you have the sample, and the enemy doesn't have it.
But then they can also get your sample, right?
No, because wirelessly I'm delivering. I'm connecting the B-static 1, 2, 3, 4, 5 kilometers away, and I'm doing it.
No, so the question is that if you have a dual blind deconvolution at your receiver, then you mentioned that your enemy can also use that. But the enemy can only use it if they get these signals from us, right? So if they get these signals from us, they can also get the direct signal as well.
They have a receiver. If they install the receiver near the airport, without you knowing, they are getting the information. Okay.
Yeah, but okay. All right. So so let's look into this trigonometric polynomials, but a specific variety, that is positive trigonometric polynomials. But because we are in higher dimensions, it is positive hyperoctane trigonometric polynomials. That's just a matter of detail. So a trigonometric polynomial, if it is non-negative on a unit circle, so you can think of it as a DFT, just to visualize it, but it could be very general trigonometric polynomial as well. So we have this very important result. So Professor Bogdan Dumitrescu in 2007 published this very popular book, now a second edition is out, on positive trigonometric polynomials and their signal processing applications. And this theorem comes from there, which says if you have a positive trigonometric polynomials, then its coefficients Rk, so Zk are the exponentials here. So the coefficient Rk, you can parameterize them using these two types of matrices. One is this elementary Toeplitz matrix, and second is the Gram matrix. Now, what is the importance of this result? If you get an inequality on a trigonometric polynomial, like it is greater than or equal to 0, or some other type which you can convert into a positive trigonometric polynomial inequality, then you can characterize that inequality using a linear matrix inequality. Using an LMI, you can describe that inequality. The import of this result is, as we'll see in a moment, when I start from this primal optimization problem, one way to attack it is, because I don't have a straightforward way to get an SDP, is to convert to its dual. And when we convert it into dual, then we get these kind of inequalities involving positive trigonometric polynomials, which then we convert to LMIs. Once you have LMIs, then you get a semi-definite program. Okay, and as I mentioned earlier, we use the term PHTP for the multidimensional cases. So let's start with that. Now, we had the primal optimization problem, and the constraints were all equality constraints in that. So we go into optimization theory, then if you have equality constraints, then you write the dual, and then the strong duality holds by Slater's condition. That means if you solve the dual problem, you also get an exact solution to the primal problem. So we had equality constraints in the primal problem because you had just the measurements, y equal to Aleph, R, etc. Right? So we are going to look into just the dual. So again, some pages of tedious algebra, and you get this first equation, which is the dual optimization problem. Its constraints for radar and communications, they involve the dual of atomic norm, and if you take 1 minus that term, the dual of atomic norm, greater than or equal to 0, it turns out this 1 minus dual of atomic norm is actually a trigonometric polynomial. So you get a PTP in the constraint. So we use the result for Dumitrescu, and we convert those inequalities into linear matrix inequalities involving these Gram matrices, which is the second equation here. Once you have this equation, this is the semi-definite program. Now you can code this. And as a result of solving this, you will get two polynomials, one for radar, one for communications, that is FR and FC. Those are the trigonometric polynomials you'll get. Okay, fine, we have solved this, but how do we get these channel parameters out of this? That is the question, right? How do we get velocity? How do we get delay, etc.? So, in our paper, we derived these very strong theoretical guarantees, and I've summarized them here in this slide. But just to give you an idea of what this means. So you get two polynomials, FR and FC. What these guarantees tell us, you plot the absolute value of those polynomials, because they are polynomials in delay and Doppler. You plot them in delay and Doppler plane, and wherever the maximum modulus achieves unity, that is the location of the target or the this channel parameter. That means exactly unity within certain numerical precision. You can compare this with the so-called CFAR detector that is used in radar signal processing, where once you have the signal, a post-process signal, then you compare its strength with certain threshold. If it is above that, you declare it as a target. If it is below that, then it is clutter or noise. Here, we are saying it should be exactly unity to declare the presence of the target or certain channel parameters. That's what we show here. We are plotting these polynomials in delay and Doppler plane. And then the green circle in the zoomed out portion, that is the location of the true targets or true channel parameters. And then we mark the values which are where this maximum modulus achieves unity by the plus sign. And you can see plus is right on top of that green circle. So this is how you get the channel parameters, delay and Doppler. Once you get the channel, then like you said, if you can apply standard techniques now, because you know two convolvents now, then you can apply least squares method or any one of your favorite methods to estimate the signals. So that part is straightforward. You can find more details in some of the papers that I've listed here. Now, there are so many variations of this problem. Presence of noise. If you have presence of noise, then you have to add a penalty function to that optimization problem. You can find the exact expression of that penalty function in our papers. What about n-tuple blind deconvolution? So if you have several emitters, 3 radars, 4 communications, then the number of LMIs also increase. Okay, so you'll have 3 plus 4 LMIs in your optimization problem. What if radar and communications, they are not synchronized in their transmission and there is some delay, and again that delay may also be unknown, then that unknown becomes another parameter while solving this dual blind deconvolution problem using the LMIs. So you estimate that as well apart from your other unknown parameters. So several variations. Atomic norm minimization SDP could be computationally intensive. So in some of our recent works, we have suggested some alternative algorithms which have lower complexity. So there is that area to explore as well. Okay, so that was an example of spectral coexistence and to show you that how some new and very interesting signal processing theories, they come into play in these kind of examples. Now we take the second topology, which is spectral co-design. And here I am going to take an example of automotive joint radar communication. So recall in spectral co-design, there is some sharing of hardware, right? And common waveform may also be involved. So here we start with that bistatic scenario that I had shown earlier. And as I mentioned earlier, this is more common because if you're transmitting in a crowded traffic, most likely the signal can be intercepted by other receivers. Apart from that, there is another advantage. If the transmitter and receiver of the radar, they are on the same vehicle as shown in the monostatic case, then the coverage of that radar is that red circle that you see on the bottom right. It's a circular coverage. But when it is a bistatic scenario, then the coverage is an ellipse. So in one direction, you get range extension. So you can actually sense at a far greater range than a monostatic case. On top of that, if you look into the bistatic diagram, then the receiver and transmitter, they don't have a line of sight. There is this blue car in between the red and the gray car. But in a bistatic case, it can help in this non-line of sight sensing or communications as well. So even if there is no direct path, you can still extract the parameters of the blue or the yellow car. So that is another advantage of this. This paper appeared in Transactions on Aerospace and Electronic Systems. It was a runner-up for the IEEE Barry Carlton Award last year. And in this paper, we look into two major aspects. In any kind of ISAC problem, typically researchers explore which waveform to use, because there are waveforms that are suited for radar purposes, and then there are protocols which are suited for communications. If you want to use just one waveform, then there's always a question which waveform to use and how to use that waveform, which is optimal for both of them. You can also design a completely new waveform, but then you may not have chipset or a supporting hardware for that completely new waveform. Especially in the automotive industry, people prefer to use one of the known waveforms so that they can use existing chipsets for that particular waveform. So design of waveform is a very important aspect. Second aspect is exactly what to optimize. So we saw some examples like radar-centric approach or communication-centric approach. And the third aspect is, having transmitted a common waveform at the receiver, how do you separate radar information from communication? So we had that example in spectral coexistence, but there the waveforms were different. Now we'll use just a single waveform to do this. Yes?
Did you look at the impact of multipath?
In this problem, no, not in this problem. Yes, but I'll provide a reference where you can look for that. Yeah. So in this work, we first started with which waveform to use. So we start with one radar waveform and then a communications waveform, and then we wanted to check how they perform in a joint radar communications mode. So for radar, we choose phase modulated continuous wave. It is very popular, and now IMEC has released chipsets for PMCW. It's a company based in Belgium. They have released PMCW automotive radar chipsets now. So it has a very wide bandwidth. Wide bandwidth means high resolution, as we discussed earlier. So we are going to use PMCW for the radar-centric waveform. For communications, we are going to use OFDMA. Now, if you use these waveforms in standalone mode, PMCW has a very good performance in estimating the range of the target. OFDMA can estimate Doppler very well. Now, we wanted to see how they perform in a joint radar communications mode. One way to investigate this aspect is you look into the ambiguity function of the waveform. For people who may not be familiar what ambiguity function is, you take a transmit waveform and then you correlate it with itself with its delayed and Doppler shifted replicas. The result is the ambiguity function. It will have a main lobe and then some side lobes. Lower the side lobes, it's better, because then you can distinguish two very closely spaced targets very well. So we derived the joint radar communications mode ambiguity function for each of these waveforms. You can find the derivation in the reference that I've cited here. So what do we see? When we examine this JRC mode ambiguity function, it turns out that these children waveform, they retain the properties of their parent waveform. PMCW JRC has a very good performance in range estimation, and OFDMA has the same in the Doppler estimation case. Okay, so now we transmit these common waveforms. How do we separate them at the receiver? So here's the receive processing. I'll just summarize because there are a lot of equations, exactly what we are doing here. So at the receiver, you transmit the PMCW waveform, it interacts with the targets, comes back to the receiver, and then you have these four unknowns that you would like to estimate: range, Doppler velocity, and direction of arrival of the radar target, and communications messages. In PMCW JRC, it turns out the direction of arrival estimation you can do with simple beamforming. For range estimation, you apply matched filter and you get very accurate estimate of range. Then you're left with Doppler and communication symbols. It turns out in the signal that is left over, you cannot estimate these two things accurately because they are coupled together in the residual signal. So an independent estimation is not possible. It will be highly inaccurate. So in our paper, we explain how to deal with this. We suggest some kind of multiplexing. That means for some frames, you transmit radar-only waveform. The rest of the frames, you transmit joint radar communications. Once you do that, that gives you enough identifiability at the receiver to break this coupling between the Doppler parameter and the communications. In OFDMA JRC, a very similar problem occurs, except that the coupled parameter is not Doppler, but it is range. Because if you recall, OFDMA can estimate Doppler very well. So it estimates Doppler using FFT, and in the end, it's the range that is coupled with communications. Solution, multiplexing, but now in the frequency domain. Subcarriers, we devoted just for radar only transmission, and the rest of the subcarriers for joint radar communications. Indeed, if you look at the transmitter receiver design for this kind of system, the receive processing is very similar. You have a radar processor and then you have a communications processor. In radar processor, first you do an estimation of this uncoupled parameter. Then you get information from communications processor about the communication symbols. You remove them from this residual signal, and then you estimate the coupled parameter. Now, obviously, communication symbol estimation in the communication processor can be inaccurate because it is doing that estimation on this joint signal. So, depending on how much inaccurate it is, we'll see in a bit how it impacts the performance. But again, the receive design is very similar, except for which parameter is coupled. Of course, there are two different waveforms, so that transmitter design is going to be different. The only common thing is the multiplexing part. But in PMCW, the multiplexing happens in time domain. In OFDMA, it happens in the subcarrier or the frequency domain. Here is an example that shows the advantage of this multiplexing technique. So recall that it's the range parameter that is coupled in Doppler. So I'm plotting the root mean square of range in the case of OFDMA. And in PMCW, it was Doppler that was coupled. So I'm plotting Doppler parameter mean square error, the estimation error in case of PMCW. So let's focus on figure B in this case. So the red curve in all the cases is the theoretical curve. That means the communication symbol estimation was perfect, and when you pass that information to the radar processor, it perfectly removes communication symbols and then estimates the coupled parameter. So obviously, that if that removal is perfect, the coupled parameter estimation will be very good. So that is denoted by that red curve. So we are calling it the perfect communication symbol removal. Then we have the blue curve, where we are not doing any multiplexing. Obviously, communication symbol estimation is going to be imperfect. There will be some errors. When you try to remove it, the coupled parameter estimate will also not be very good. However, at high SNR, this doesn't seem to matter. At high SNR, the blue curve approaches the red curve. But when the SNR is low, which is often the case with these kind of systems, especially radar, they are low SNR systems, then the gap between the two curves is very high. But if we do multiplexing, which is the gray curve, that is, and here we are doing half frames or subcarriers for radar only transmission, and the rest of the half is for joint radar communications. When we do this half multiplexing, and then we do this estimation of coupled parameter, then you can see that the gray curve has a better performance than the blue curve in the low SNR regime. So even though I was saying that at high SNR it doesn't matter, that situation rarely arises in practical situations. It is usually the low SNR situation. So invariably, you are going to need multiplexing to address this. Okay, so we have seen an example of coexistence, co-design. I'm not going to pick another example of co-design, but if there is interest later on during discussion, I'll be happy to discuss more. I want to now show an example of opportunistic ISAC, which is our last example. So recall that in opportunistic ISAC, you already have some communications or radar infrastructure and you want to use it for the other application, right? So here we are going to see a very interesting and practical example of using communication satellite infrastructure for weather sensing. So here's the problem that we have. So we did this problem with one European telecommunications company whose name I cannot reveal because of proprietary reason, but I can tell you what is the problem here. So if we want to estimate weather, then typically there are weather radars which do that. And these radars operate in S-band, mostly in the United States, and in C-band in Canada and in Europe. These are very big systems, very expensive systems, and in the contiguous United States, there are about 140 National Weather Service radars at S-band that provide the full coverage of the country. But as you move away from the radar, about at 80 kilometers, so theoretically their range is 250 kilometers, but right at 80 kilometers, the lowest elevation beam is already touching the cloud tops. It is not seeing anything in the lower troposphere. So theoretically, the coverage is there, but practically there are a lot of gaps in the coverage. And then the similar situation arises in C-band radars as well, which are deployed in Europe. Further, there are several regions in the world where there are no weather radars because they are very expensive systems. So we do not have coverage in many countries, especially in developing economies. So here is what this telecommunications companies approached us for. There are a lot of user terminals of communication satellites. So in a communication satellite, the signal is traversing from the satellite all the way to the ground terminal. It is passing through the atmosphere. So it may have some information about the rainfall because it is passing through the medium. As the signal travels, it interacts with the scatterers in the rain medium and it loses its strength. In other words, it suffers attenuation. The amount of attenuation is related to the amount of precipitation. So if we know how much attenuation is there, can we estimate the rainfall? That was the problem that they approached us for. Now, the advantage here is that while there are only 140 S-band radars, and that too in contiguous United States, the user terminals, there are about 300,000 of them in Europe and about 2 million worldwide. So it's a very wide coverage and very dense coverage. So that can give really good information. So how to estimate rainfall from this attenuation data? That was the problem that we started on. These satellites operate in millimeter wave in KU-Ka band. And in general, if you go by the ITU recommendations, at those frequencies, there is a linear relationship between the rainfall rate and specific attenuation. Specific attenuation is the first derivative of attenuation with respect to range. So that's the quantity we use to quantify attenuation. But that linear relationship is a very broad relationship and it gets perturbed very easily when the storms are convective, when there are huge winds and all other types of atmospheric phenomena. Then we cannot use that very simple formula to actually estimate rainfall accurately. Now, in case of weather radars, they receive a wealth of information in their received signal. So they are also transmitting two polarizations usually. So they get information such as size and shape of the raindrop intensity, how much phase propagation delay has been there. And by using all of this information, weather radars can provide very accurate rainfall rate estimate. In our case, all we have is the transmit power from the satellite and the receive power at the user terminal. And by comparing the two of them, we get the attenuation, how much attenuation has been suffered. So we don't have a lot of information to provide an exact rainfall rate. So what do? So in many presentations these days, there comes a point where you encounter deep learning. This is that point in my presentation. So we turn to deep learning. In the absence of information, our goal is as follows. We'll take a deep learning network, we'll train it with data from the nearest weather radar, and then in the prediction stage, we are going to use the communication satellite data. So we started with a very simple scenario first, where we are using this LSTM network, and we started with this region in the southwest portion of Germany, where there are about 20 terminals. We trained the network with the nearest German weather service radar data, which is a C-band radar or DWD radar in German. And then we are going to see what kind of performance we get. So just for one terminal, and the other diagram shows the satellite overpass in that region. So here is the result we get. There are two plots on the right side at the bottom. The bottommost plot is comparing the instantaneous rain rates. And you can see that the satellite link estimate very closely follows the DWT radar. But instantaneous rain rate is not what meteorologists use. They use accumulations or the cumulative rain rate. So the top plot compares the cumulative rain rate. And as you see, as time elapses, the gap between the two becomes wider and wider, right? So it's not very accurate. We would like to improve this. And we are getting some result, but we want to improve this further. Now, extrapolating a little bit from this, so we had 20 terminals. We did this kind of training for each one of those terminals, and then combining the data of all those terminals, we generate the rainfall map. Yeah, I'm concluding in 5 minutes, yes. So we generate the rainfall map. So on the right side, you see what the German Weather Service radar is seeing for one storm that is moving towards the northeast, and what our satellite link, this composite data map, is showing on the left side. So obviously, they are not very comparable. Radar is very accurate as expected, but all we see is that the relative intensities are captured and the direction of the core of the storm is captured. But for meteorologists, this is still not very useful data. So what we did is, here we had just 20 terminals. As you know, in deep learning network, when you have more data, the network performs very well. And then you also have to experiment with different types of networks. So that was LSTM. We experimented with many different types of networks. And then we got access to the data from France, which had 11,000 terminals. Now, with so many terminals, and by trying different types of networks, here is the result we get. So on the top, you see that the Meteo France radar is on the left side, and the satellite link is showing these accumulations on the right side, very comparable. And then the two bottom panels are showing every 3 hours how is the comparison. So with more data, this improves a lot, this performance improves a lot. And here is a movie that shows a storm where on the right side you see the satellite link, and all these black dots that you see, those are those 11,000 terminals, and sometimes they also disappear because there can be outage in those terminals as well. But this example shows even if there is an outage in some of the terminals, still it captures rainfall very well, the circulation patterns, and certain regions where you may not have any data because there was outage in the terminal, it can actually estimate rainfall in those areas as well. So this is a very good example of using communications infrastructure to complement weather radar. This is what we call as opportunistic ISAC, and a very practical example. Of course, it's, as I said earlier, there are so many different solutions. So we have a lot of work going on in this area covering different aspects of the problem. So some of them I've listed here, which I didn't cover in this talk. But if you come to one of our tutorials, we go into the details of many other topologies. I provided the references here, including ISAC-based VSM that is using 5G waveforms for vital sign monitoring of driver and other passengers. Some more architectures are listed here. When you open the spectrum to be shared between radar and communications, then especially for military radars, the security of radars and the privacy of communications users could be compromised. So there is a lot of focus lately on designing secure and privacy preserving ISAC. We have also done some work. You can find more details in these references. So at the end of every YouTube video, you have like, share, subscribe. Now, this is not a YouTube video, but if you're interested in my research, then please feel free to connect with me or follow me on LinkedIn at this handle, where I regularly post updates about my papers and upcoming talks. We have a book that was published this year by Wiley IEEE Press, Signal Processing for Joint Radar Communications, where you can find a lot of detail about the topics that I discussed, and way more than that. As you would have guessed, one of my areas of interest is weather radar. So we have recently published a 3-volume compendium last year in December, which covers advances in weather radar, many interesting applications in last 10 years. So with that, I would like to thank you for coming to this talk, and I'm glad to take any questions you guys might have. Thank you.